Ladies and gentlemen, good morning. I am very glad that I can welcome you to this colloquium with Nobel laureate Jerome Friedman. My name is Peter Krauss. I am the Vice Rector for R&D at the University, and I will moderate this colloquium. I hope you have attended some seminars with Nobel laureate, and I hope that you enjoyed the seminar. In this lecture, Professor Friedman will talk about the science behind the work that earned him the Nobel Prize. Professor Jerome Friedman is an institute professor and professor of physics emeritus at the Massachusetts Institute of Technology in the United States. Born in Chicago, he excelled in art and was offered a scholarship to the Art Institute of Chicago Museums. Although he loved art, he turned down the scholarship after reading Relativity by Albert Einstein, and he fell in love with science and studied physics at the University of Chicago, where he received his PhD. Professor Friedman carried out his doctoral research under the supervision of Nobel Prize winner Enrico Fermi, an Italian physicist who is credited with the creation of the first nuclear reactor. During his career at MIT, he has conducted research studies of particle structure and interaction with high-energy electrons, neutrons, and hadrons. Because of his work on the innermost structures of matter in 1990, Professor Friedman received the Nobel Prize in physics for pioneering investigations concerning deep inelastic scattering of electrons on protons and bound neutrons, which has been an essential importance of the development of the correct model in particle physics. He is a member of the National Academy of Science, the American Academy of Art and Sciences, and the American Philosophical Society. Now it's my great pleasure to welcome Professor Friedman to the stage.
Thank you very much. Thank you very much for your kind introduction.
Well, can you say that there are seats and anyone should find their seats so they don't have to stand?
Oh yes, please. Yes, there are probably seats here. We shouldn't have people standing. So
Seat right here.
it's great. It's a great observation.
Sorry.
No, don't. I think that's wonderful that you. So today I want to talk about basically the whole range of physics, starting from the smallest dimensions that one can observe and study, and even think about, to the entire cosmos. And physicists study all of these, and it covers roughly 60 orders of magnitude. You know, when you really think about it, one discipline covering 60 orders of magnitude, that's really incredible. And so what I really want to do is talk about the general ideas. I want to avoid mathematics. I don't want this to be too technical a seminar. I really want to give you a sense of what the ideas are, what the progress is, what the remaining questions are. And of course, there are many, many questions that are unresolved. So basically, I want to start with cosmology and experiment. Experiment in cosmology is primarily observation. And here, you know, we have the cosmic rays here. We have the Hubble telescope. It's about the size of a school bus. We have specialized satellites. This was WMAP, one of the early satellites which gave enormously important information. Here's a radio telescope. There are vast arrays of these things to actually get radio waves from distant objects in space. And here's a observational ground telescope. So these are all the devices that are used to essentially get the information that is used in developing cosmological models. So what is cosmology? How do we come into being? Why does the universe look the way it does right now? And what will happen to it in the future? And when you these are the questions that cosmology wants to address. And the basic idea is to use general relativity as a framework, and that is the framework. However, when you think about the evolution of the universe from the Big Bang on, you have to put into it particle physics and nuclear physics. So all these things are included in trying to develop cosmological models. Now here's a beautiful picture from the Hubble telescope. Now each one of these lighted areas is a galaxy. It's a galaxy. This is a deep probe picture. And it's estimated there are about 100 billion galaxies in the universe. And the universe is the part that has expanded out into space since the Big Bang. And if you look at each galaxy in particular, for example, here's a spiral galaxy. There are roughly about 100 billion stars in a galaxy. So it means that the estimate is that there are 10 to the 22 stars in this universe. And yet, if you ask what percentage of the total mass or mass energy, you see, when I talk about mass energy, since mass and energy are equivalent by equals mc squared, so let me just talk about energy in particular. The stars constitute less than 1%. It's a small fraction of 1% of all the energy in the universe. So the point is that we have now the Big Bang model. There was some sort of event that occurred 13.7 billion years ago. It's pretty precise in terms of the time that they've been able to observe. And what's happened is that the universe has been expanding ever since. And you can actually, measure the so-called redshift of various stars and find out how far how fast they are receding from you. And the further a galaxy is from you, the faster it's receding. And so so now it turns out that the edge of the universe that started at the Big Bang is now 46 billion light years away, 46 billion light years away. And now a light year is about 5.8 trillion miles. So it's a gigantic universe. It's a really gigantic universe. And the thing is that, you know, what's remarkable, when you have 10 to the 22 stars, and we're just a tiny little planet with one star, you know, the Earth is less than a speck of dust in the universe. Oh my goodness. There's a place to sit. Yeah, I'm sorry. Yeah, that's good. And so actually, in terms of finding out the distance of a star from us, there are so-called standard candles in the universe, which are special kinds of supernova, which basically have almost a very uniform delivery of light, and therefore we can use them to get distances, and we can use the redshift to find out how fast these things are moving, and then we have something called the Hubble constant, and so once you know the Hubble constant, and you can find out the velocity by the redshift, therefore you can find out the distance of a particular galaxy from you or a star. Now, let's talk about the various periods after the Big Bang. So things happen very, very rapidly according to the cosmological model. 10 to the minus 35th seconds after the Big Bang, the temperature was 10 to the 27th degrees Celsius. And it was at this point that all the fundamental particles were starting to be produced. For example, there was a tremendous amount of radiation and the radiation created pairs of quarks, pairs of electron positrons, et cetera, et cetera. Now, at 10 to the minus 6 seconds, what we have here is that neutrons and protons were formed. You see, what happens is that the universe was extremely hot when it first formed, and it started cooling down very, very rapidly, and that is at 10 to the minus 10th degrees Celsius. And so it's like having various gases mixed together, and then as the temperature decreased, different gases basically condensed out into a more, for example, a liquid or something of that nature. So what you do is, when the temperature got low enough, neutrons and protons were formed, and then in 3 minutes after the Big Bang, nuclei were formed. So that's 3 minutes. You know, this is remarkable that this kind of time scale occurred. However, it took 380,000 years for atoms to form. Because of the energy levels of atoms, they had to be, it had to be relatively cool for atoms not to be basically torn apart by the radiation. And then basically, sort of 400 million years after that, when it was about 200 degrees centigrade, and we're talking about the radiation field for the temperature, stars started forming, and then you started getting galaxies in about 1 billion years. And here we are at 13.7 billion years, and we have all these galaxies around us, and we're here on the Earth. And the universe is very, very cold. It's, at this point, it's now 2.735 degrees. It's measured very accurately, Kelvin, and that's absolute, above absolute zero. And that's where we are now. And so it's a very interesting scenario, and this is the current scenario of cosmology today. Now, I want to point out that accelerators basically recreate the conditions of the early universe, and that's why they're so interesting. For example, Fermilab, which had a total energy, it was a colliding beam accelerator. It's no longer in operation. It was 2 trillion electron volts, and that was able to actually simulate the conditions of the 4 trillionths of a second after the Big Bang. And now the LHC, being a somewhat higher energy accelerator, is closer to about 1 trillionth of a second. So you actually recreate the conditions of the universe at that particular early time. Of course, this is a very late time compared to this very, very rapid development, but nevertheless, it's extremely interesting. Now, as I said, there was a radiation field, and the radiation field basically, as the universe cooled down, we got longer and longer wavelength radiation, and that's been measured to great accuracy. And this is the black body curve right here. It's one of the best black body curves ever measured, and it's amazing that it comes from space. And this is what gives you this very, very accurate temperature. Okay. So here's the WMAP satellite. It's a very early one. It basically had 20 differential radiometers, and what it did is it measured the intensity at different frequencies of the radiation field. And this was a very, very important device because it got some enormously important information about the types of energy that exist in the universe. And this is an interesting thing. It measured the variation of temperature. Now this is the entire universe as it measured it in all directions. And if you look down below, the color scheme here This is minus 200 to plus 200 microkelvins. So that's an extremely narrow range of temperature. And you can see here how uniform the temperature of the universe is. And that's one of the remarkable properties of the universe, that the temperature is so uniform. And because it's so uniform, one had to get some mechanism to make it so uniform. And this is where the inflationary model, which I don't have time to discuss in detail, comes in. At some point, the universe expanded enormously rapidly, starting at about 10 to the minus 35 seconds. And because of that, it was able to develop a very, very uniform temperature distribution. But from this variation, one can learn a lot. And this is what one has learned. One has learned, see, here we have billions of years. Here is the relative size of the universe. We are here now, and you can see that roughly about 25, or no, I would say about 22 billion years from now, 22 billion years from now, the universe will be 4 times its size. You can see the top curve, which basically does this. Let me just, this curve right here is the curve that corresponds to the measurements coming from WMAP, the satellite. And you can see that not only is the universe expanding, but the expansion is accelerating. And this was a surprise, but it hadn't been confirmed. And it was later confirmed by a very important experiment which looked at standard candles, which were special kinds of supernova out in space. And they could actually demonstrate observationally that the expansion is accelerating. And that's a very interesting thing. So you see, in the early days, people thought that maybe, for example, this lower model here, where the universe does this, basically it goes out to a certain size and then it comes back, and it's what they call the big crunch. But there was not enough matter and energy in the universe to do that. The amount of matter and energy in the universe was insufficient to have the big crunch occur, and so the universe will be continually expanding and ultimately just become a very, very cold universe. Even the black holes will disappear ultimately because the black holes radiate away their energy in Hawking radiation. So I don't have time to get into that, but even the black holes will disappear, and it'll be a universe dominated by very, very cold radiation. The temperature will be very, very low, very, very close to absolute zero. So the question is, what is the energy content of the universe? And it's very interesting. If you look at the universe, and we're made of atoms, which I discussed in detail yesterday, and less than 5% of the energy of the universe is in atoms. There are 2 other areas, types of energy. One is so-called dark energy, which we have no idea what it is, but that's the majority of energy in the universe. WMAP said it was 73%. And then there's something called cold dark matter. That's, according to WMAP, that was a 23%. And so what we have here is we have a situation in which we only understand roughly about 5% of the energy of the universe. So most of the universe is totally a mystery, a big, big mystery. And you know, this is something for the students here to help resolve in the future. This is not an easy question. What is this dark energy? I want to say, now there was another satellite which I didn't have time to discuss. It's the second version of such a satellite, but a much more sophisticated one. It's called the Planck Surveyor. It was sent up in 2009, and it's produced incredibly good data. And I didn't show that because I just wanted to show the historic development. But the data is much more precise than WMAP data, but fundamentally agrees with it within experimental error. So, and here's a picture of its launch. It's very impressive. But, so what do we know about the contents of the universe? So, dark energy, as I said, it's a total mystery. In fact, when the particle physicists try to figure out what it should be, based upon what I call the field theory models, they're off by 120 orders of magnitude. That's a big error. So we don't know anything about this. It's quite clear that this is a big mystery. Now, dark matter is another matter in the following sense. It's probably some exotic particle which has not been discovered yet. It's not made up of atoms, as I said, but it's some exotic particle. And some people think that it may be discovered at the LHC. And I'll say a little bit more about that later. So now, so the other matter is atomic matter. And this, now we're getting to the small sizes of the universe, the small structures. And the research in the 20th century produced a tremendous amount of information about atomic structure. I actually will cover some of the material I covered yesterday. I'm sorry for those of you who were at the lecture, but I'll go over it very quickly, and I'll show some different facets of it. So we have research. I think I talked about this yesterday, that the whole idea of getting more and more magnification into your observations. I think I discussed this yesterday, so I won't spend. How many people were not at the lecture yesterday here? Okay, I'm sorry. So you can actually. The whole idea here is to have higher and higher magnification so that you can actually look at the various components of atomic matter. You have the atom with electrons going around a nucleus. You have a nucleus consisting of neutrons and protons, and then you have basically quarks that basically are what make up neutrons and protons. And of course, the tools for investigating subatomic world are particle accelerators, particle detectors, scattering experiments which probe particle structure and forces. And the idea also is to produce new types of particles which have not been observed since, or not been present since the very early universe, except for those caused by high energy cosmic rays. So I talked about a particle telescope, and this comes from quantum mechanics, that basically particles have wavelengths. In order to see something small, the wavelength must be considerably smaller than the thing that you're looking at to get a reasonable resolution. And so therefore, given the de Broglie wavelength, which is equal to Planck's constant over the momentum, the higher the energy, the smaller the wavelength, the smaller the object you can actually observe and study. And so basically, after the war, there were many particles discovered. They were organized into a so-called eightfold way based upon a mathematical model called SU3, it's unitary symmetry model. And it was a periodic table of the particles, just as we had a periodic table of the elements. And it was predictive as well as descriptive. In other words, many of the particles fit in this model, into this classification scheme, and many particles were predicted and they were ultimately discovered. And let me show you the classification scheme. This is the periodic table. So this is something I didn't show yesterday. And these are the various families. And each one corresponds to a certain spin particle, and every little node there corresponds to a particle, and every one of those particles was discovered ultimately. Some were very difficult to discover. I discussed yesterday the family on the right. It was the so-called spin equal 3/2 family, and the omega minus was a very difficult particle to discover, but it was ultimately discovered. And this thing, it was just absolutely amazing. Nobody understood why the SU3 should work. And so it turned out that in 1964, what Gell-Mann and Zweig independently understood was that a triplet could generate all these families in terms of this mathematical model. And this triplet corresponded to 3 quarks. Up, down, and strange, they all had spin 1/2. They had fractional charges. The up was 2/3, and the down was minus 1/3, and the strange was minus 1/3. And the baryons, which are the heavy particles like the proton and neutron, consisted of three quarks, and the mesons, which you probably have heard of, the pi meson, the k meson, these are various particles that are created at accelerators. They consisted of a quark and an antiquark. And a proton consisted of 2 up quarks and a down quark, and a neutron consisted of 2 down quarks and an up quark. And that was the idea. These particles were ultimately discovered by an MIT SLAC group at the Stanford Linear Accelerator using the equivalent of a very high-powered electron microscope. The constituents were discovered inside the neutron and proton. And as you can see, as I said yesterday, the magnification was 60 billion times that of that you can use that compared to ordinary light. And so here's the linear accelerator. I won't spend much time on this. I spoke about it yesterday. Here are the detectors that were used. And the idea was that in the old physics, the electron would barely scatter. The idea was that the proton, for example, was a blob of charge. And so something going through it would barely scatter. If you had constituents in the proton, for example, quarks, the electron could scatter off these particular constituents. And for example, since the quark was about 10 times heavier than the electron, it could actually bounce off to a pretty large angle. And so but here was a very important aspect of it. So, somebody asked the question, how could you see anything with all the complications occurring when you have inelastic scattering? And this was in inelastic scattering, the electron comes in and shatters the proton. So the question is, how do you see anything that's clearly? Well, if you look at the uncertainty principle, you can see why it works. What you really want to do is to have a snapshot, a very, very fast shutter speed on your camera, effectively. And you see, if you look at the uncertainty principle, delta E times delta T is roughly equal to, at its smallest limit, H, Planck's constant, for example. And if you have an energy loss of about 2 GeV, and let's say the constituents in the proton are moving with the velocity of light, you can show that the snapshot occurs in 10 to the minus 14, 10 to the minus 25 seconds. I'm sorry, 10 to the minus 25 seconds. And if you say that the constituents are moving roughly with the velocity of light, then it says the snapshot basically, there's a little bit of fuzziness, which is 10 to the minus 14 centimeters. But since the proton is 10 to the minus 13 centimeters in radius, then you have a good chance of seeing something inside the proton. And that's the way it worked. And this, of course, was a very unpopular approach. People thought it wouldn't work, but it's the only way to see constituents in the proton. And that was used in this experiment. See, the other approach is to use so-called elastic scattering, where you basically don't break up the proton at all. And in that case, unfortunately, because in the center of mass there is no energy loss, you are taking a very, very long time exposure. And therefore, a constituent moving around very fast just gives. And so here is the scattering distribution. Now, at the bottom is momentum transfer. This is the momentum transfer that the electron gives to the proton. Basically, it's really, this is the so-called four momentum transfer, which is relativistically invariant momentum transfer. And the thing which is interesting, if you use the old physics, the blob of charge, you get this lower curve. And then but what was observed was all these points above, and you can see the enormous difference in the scattering probability. The vertical axis is the scattering probability. And so there was no question that there were constituents in the proton. So let me just show you what happened. So in 1968, point-like constituents were found in the proton by the scattering. And when I say point-like, what I'm saying is that when you reconstructed the image of the little things that you were scattering from, you couldn't tell what the actual size was. You could only tell what the upper limit of the size was. So in 1971, the measurements of backward and forward scattering showed that the spin of the constituents was 1/2. And then in 1972, a comparison of electron nucleon and neutrino nucleon scattering indicated the fractional charges of the quark. So the quark model was established as being valid in 1972. So, but this required a new theory to explain what the experiment produced. It was called quantum chromodynamics. It was developed by Wilczek and Gross and Politzer independently. And the thing about this was that the force between two quarks was roughly constant as you pull them apart. Now, when you have interactions between particles, there's something called an interaction constant. Let's say alpha sub s. And this comes from the theory. You notice that it's 1 over the log of something called q squared over lambda squared. And lambda was just a constant. Q squared is a momentum transfer. So what you see here, which is interesting, as the momentum transfer gets bigger, the coupling constant, or the source of force, gets smaller. So the higher the energy, the weaker the force becomes in terms of the interaction constant. And this was really quite surprising. It was a new type of theory, and it had to be tested. And so here's the test, and here is alpha up there on the vertical axis, and here is momentum transfer, and you can see that the theory is basically validated by experiment. So QCD, quantum chromodynamics, which was developed to actually make the whole quark model acceptable, has been verified in numerous experiments. And you might say, one of the great questions was, as I pointed out yesterday, is why can't you find free quarks in nature? And this theory will indicate why you can't find free quarks in nature, because if it gives rise to a force which is roughly constant, separating the two takes more and more energy, And the amount of energy required to even separate by 1 centimeter is 10 to the 13th billion electron volts, which is an incredible amount of energy. So quarks cannot be freed. You cannot find an individual quark in nature. So now we have all these quarks. We have 6 different quarks: up, down, strange, charm, bottom, top. The mass of the top quark is enormously large. We don't understand why these masses are so different. They all have fractional charges, which was a great surprise. All have spin 1/2. And the size of the quarks is less than 10 to the minus 17 centimeters. So they're incredibly small. They're probably much smaller than 10 to the minus 17, but that's as well as we can measure. The LAC will probably give a limit of maybe 10 to the minus 18th or centimeters. But for every factor of 10 in energy, you get a factor of 10 in magnification, and you get a factor of 10 in the limit. So what do we have here? That we have right now, these are the fundamental quantities. These are the basic building blocks of the universe in terms of atomic structure. We have the 6 quarks. We have 6 leptons. Now, the leptons, we have the electron, which you know about. The mu and the tau lepton are just heavy electrons. We don't know why they exist that way, but they're heavy electrons. And then each lepton has an associated neutrino. So there are 3 types of neutrinos. There's an electron neutrino, a mu neutrino, and a tau neutrino. And so we have now a standard model which involves 3 forces: the so-called strong force, that's quantum chromodynamics, the electromagnetic force, which you know all about, and the weak force, which basically has to do with radioactive decays. Now, as you well know, when you have a force field, there is an associated particle, because quantum mechanics always associates a field with a particle or a particle with some sort of field. And so, for example, the strong force has a gluon associated with it. The electromagnetic force has something you've heard about all the time, a photon. The weak force has 2 different types of particles called vector bosons. And one is the W particle, which is a W plus and W minus, and a neutral particle called the Z0. And these are quite heavy particles. They're of the order of 80 to 90 times heavier than a proton. And then we have gravity, which is not part of the standard model because we don't understand how to incorporate gravity with quantum field theory or quantum theory in general. So that's what we have in terms of our understanding of the universe. Now, what about the strength of these forces? First of all, if I call a strong force 1, the electromagnetic force, and this is now, what I'm doing is I'm putting let's say two protons side by side, separated by about 10 to the minus 13 centimeters. And I say this is because these forces change very rapidly with distance. But basically, in a nucleus, protons and neutrons are separated by roughly 10 to the minus 13 centimeters. And so if the strong force is 1, the electromagnetic force is 10 to the minus 2. The weak force, you can see why it's called weak, is 10 to the minus 13th. And then the gravitational force is 10 to the minus 38th. And you can see how weak gravitation is compared to these other forces. Now, the irony is that in the universe, the greatest forces that can ever be observed come from the gravitational force. Black holes. They can compress something to almost to a point, anything. So the question is why? Well, the reason why is because you don't have any anti-gravitational particles. All the other forces basically are limited. nothing limits gravity. So you keep on piling material mass in, and the force gets bigger and bigger and bigger until it overwhelms everything. And that's one of the already. The weakest here is the strongest in the universe. And the point is that the strong force decreases with energy, as I mentioned, and the electromagnetic force and the gravitational force and the weak force increase with energy. So those forces, as you get more energetic particles, those forces increase somewhat as the other one decreases. And here is the distribution in terms of space of the forces. The it's a log-log plot, and it's kind of complicated, but what you'll see here, the point is that the weak force, when you get very close in, is not so weak. But when you get a little distance away, it falls off very, very rapidly, and the reason for it is because of these heavy bosons which carry the force. On the other hand, the gravitational force just keeps on dropping. The electromagnetic keeps on dropping. And the strong force basically drops off after roughly 10 to the minus 13 centimeters. And the reason for that is because, for example, in the proton, there's something which I didn't mention. It's called color. Now, these things get very complicated. I'm sorry if color is called it's equivalent to the charge for electromagnetic. Color carries the force field. The force field comes from color. And if you have a proton or any particle, the color is white. Because each quark, let's say in the proton, you get red, blue, and green. So you basically, they cancel each other out and you get white in that framework. And so therefore, when you get outside the proton, you get very little force from the strong force. And of course, if you have a meson, which is a quark anti-quark, so let's say one quark is blue, the other quark is anti-blue. So that cancels. So the strong force never gets out beyond 10 to the minus 13th centimeters. And that's one of the, but inside, it basically falls like 1 over r squared. So those are the properties of the forces. Now, the other point I want to make is that empty space is not empty. We have one of the major things that is fascinating in particle physics are so-called virtual processes. Things that can occur in the vacuum just spontaneously, a pair being produced and then annihilating. And you say to yourself, how can that be? How do you conserve energy when you do that? Well, you conserve, if you're within the uncertainty principle and it's there for a very short time, the energy is, you can conserve it. And so basically, the vacuum, which we think is really empty, has fields, it has virtual things occurring all the time. Now you might say, well, show me. Show me. Well, there's something called, and it's been observed, the Casimir force. How many of you have heard about the Casimir force? Okay, the Casimir force basically, if you take two conductors, for example, and separate them by just nanometers, there's a force attracting them, and it comes from these fluctuations. And so let me point out something. Imagine I put a spring between these two, and if I do that, I will compress the spring because there's a force between them. If I compress the spring, I put potential energy into that spring. I have changed the state of that system. So now, because of these vacuum fluctuations, I have changed the energy state of that system because now the potential energy in the spring adds even to the mass. If I weigh those two conductors with the spring, once I compress it, it's somewhat heavier because that particular potential energy is equivalent to mass. And so the point I want to make is that these fluctuations can change the energy of a system. And if you go into very sophisticated calculations of the energy levels of the atom, these things also will change the energy level slightly. And that's, maybe you've heard of the Lamb shift, things of this nature. And this comes from virtual processes. These are called virtual processes. So let me talk about the theoretical developments. So there was electroweak unification in 1967. It was a way of relating the electromagnetic field to the weak interaction. And then quantum chromodynamics was developed in 1973. It was 1 year after the discovery of the quark. And the combinations of these two theories is called the Standard Model. You probably have heard the Standard, but this is what the Standard Model is all about. And so let me tell you about the unification. So if you have a neutrino, for example, scattering from a quark, and this would be a weak interaction, it's got to exchange something. And what it has to exchange is something neutral, right? Because the quark doesn't change sign, charge, and the neutrino stays neutral. So that will be moderated by the so-called Z0 boson. On the other hand, I can change one type of quark to another, and that question came up. And that will be done by, for example, a neutrino could become a muon, and it sends a charged particle, and therefore that charged particle can change the quark from an up quark to a down quark, or a down quark to an up quark, depending upon whether the W is a plus or a minus. And that's how the weak interactions work. And then, of course, you just have ordinary electron scattering. If an electron scatters from a quark, it exchanges a photon. And now the unification took these three processes and actually connected them, and in terms of one particular constant called the weak angle. Sometimes it's called the Weinberg angle sometimes. But in the process, something has to be done, and the Higgs particle had to be brought in. And so let me explain what the Higgs particle is all about. In making some of these theories, use symmetry principles. And one of the symmetry principles used, this is technical, but I just want you to get the idea. It's not important that you know exactly what this principle is. It's called local gauge symmetry. And the idea there is you change the phase of wave functions with something which depends upon x. And then you develop structures of theories from that. But when you do that, you can only use the symmetry if you assume all the fundamental particles have zero mass. Because if they have mass, you break the symmetry. Because we know the particles have different masses. The muon is different from the electron. Different quarks are different. So you have to have something which has zero mass. But we know that in nature, these things don't have zero mass. So what you do is you get the structure of the theory, and then you provide a mechanism to create mass. And that's where the Higgs comes from. And that was the whole process. So let me then go to the next slide. And so what you do, what was done is you say, well, the whole universe is filled with a new field called the Higgs field. And these massless particles have an interaction with the Higgs field. And the interaction is such a nature that it repels their motion. It's like going through a viscous liquid like honey, for example. And so, different types of particles have different resistive forces. And so the idea is the bigger the force, the higher the mass. Because look at, if I have to push something through a viscous liquid, what am I doing? It feels as though this thing has inertia. And if you have inertia, you have effectively mass. So that's the way it was. And so the question is this was actually the simplest model for putting mass into particles. And so, but the question is this a correct picture? And of course, in physics or in any other science, the only way you can determine whether it's correct or not is to do experiment. So the point is, remember I said every particle has a field and every field has a particle. So there should be, if there's a Higgs field all through nature, there should be a Higgs particle. And that should be searched for. And they searched for the Higgs particle at the Fermilab, but unfortunately the energy was too low. But at the LHC, it was found. So let me point out a few things about the LHC. In the early days, we used to have what these called fixed target experiments. You would have a beam which would hit a stationary target, you hit a stationary target, and the question is, how much energy is available for new physics? Not all the energy put in. The amount of energy that's available goes as the square root of 2me. So basically, it's the square root of the energy that's available. And you might say, why isn't all the energy available? You know why all the energy is not available? Because you have to conserve momentum. And when you conserve momentum, you use up some of the energy in conserving momentum. And so therefore, when you have a fixed target experiment, you only can use the square root of the energy that you have produced, which is kind of inefficient in a way. However, if you have a colliding beam experiment, it turns out that the energy of each beam is available. So 2e is available. Now, and why? Because the momentum is 0 coming in, and you don't have to conserve momentum. All the particles come out symmetrically, and they basically conserve momentum automatically, and they all have the appropriate, they all have the energy you've put into the process. So colliding beams are much more effective and much more in terms of going to the very highest energies and studying things. So here is the Large Hadron Collider. It's 27 kilometers in circumference, biggest accelerator in the world. It was designed for 14 trillion electron volts, 7 in each beam. At this point, they're going to be running at 13.5. And here's the way it works. These two beams go counterclockwise to one another, and they collide. It's the two detectors. There's one detector called CMS, one over there called Atlas. And these are enormous detectors, and I'll point them out. Oh, here we have it. Here is the tunnel, which has thousands of superconducting magnets, which it's an incredible accelerator. And here's, for example, the Atlas. It's 46 meters long, 25 meters in diameter, 7,000 tons, incredibly big. It's close to 7 stories high. It's just 100 million channels of detection, incredibly sophisticated. Here is the second one. This is called the compact muon solenoid, and this is 21 meters long and 15 meters in diameter, and it's 12,500 tons. And as I pointed out yesterday, in comparison, the Eiffel Tower is 7,000 tons. So this thing is enormous in both size and weight. And again, this has 100 million channels of detection. And now the question is, how do you find out various things? We have different kinds of chambers. For example, if you want to find out that something's an electron, we see a track here, and then we have an electromagnetic chamber which has a shower. A muon goes all the way through it, just barely interacts at all. A photon does not give any signal in the tracking chamber, but gives you a shower in the electromagnetic chamber. A hadron or a pion will actually go through the tracking chamber and actually give you a shower in both the hadron calorimeter and the electromagnetic calorimeter, but it extends out there. And a neutrino is something which is kind of mysterious. It doesn't give you any signal whatsoever. And so basically, the way they do that is when you look at transverse momentum, there's a imbalance of transverse momentum, and you use that as indication that a neutrino has been emitted. And so that's the way the thing works. That's the way you select particles and you do your physics. But now here is the great challenge. When this accelerator is running at full intensity, there are about 1 billion events per second. An event is a collision which produces particles, 1 billion per second. And at that, but you can't save a billion. It's too much. So what they do is they set special conditions for observing tracks, and they try to observe roughly 100 events per second. And so you can, and of course this selection has to be made during the time of the collision, and you cannot record it on tape and do it later. It's got to be done instantaneously. It's got to be done on the basis of energies of particles, topography, all these various things. It's an enormously difficult computational task. They know how to do it. It's an enormous achievement. And you might say, well, why only 100 events per second? Well, if you run the accelerator a third of a year, that's basically that's 1 billion events per year. And these events are enormously complicated. So actually analyzing 1 billion events a year of such complication is also a very arduous and difficult task. And that's why they restricted to 100 events. But this is actually one of the simpler events. This is just a 2-jet event, you can see. And you got to take that event and figure out whether you want to save it or not. And if you do save it, you've got to analyze every particle that comes out and try to understand what's going on. So the technology that is been put into this machine and detectors is incredible. It's mind-boggling. And I thought, as an engineering university and technology university, you should really appreciate this great achievement. So this is they will produce roughly 10 petabytes of data per year, and they'll have to be processed, and it's processed all over the world using a grid. The grid will have about 100,000 computers and massive data storage devices. And I want to point out that CERN invented the World Wide Web because physicists, okay, 5 more minutes. Physicists had to communicate with one another. I have to rush a little bit now. Okay, so here's the grid. It goes across the world. All these computation centers are connected, and the data is analyzed globally. So how do you define the Higgs particle? How do you know that you can find? First of all, we don't know what the mass of the Higgs particle is, but the Higgs particle will decay into other kinds of particles. And the ratio of the decay channels will depend upon the mass. And this has all been calculated out beforehand. And for example, you can see it can go into a B quark and an anti-B quark, a tau plus a tau lepton, a tau minus, and these are tau leptons. And so you have all these possibilities. And so by looking for a peak, a mass peak in the distribution of particles, and then seeing how that mass peak decays into various channels, then you can determine whether you have a Higgs particle or not. And here is, for example, the Higgs search. This is the going into the 2 gamma channel, going into 2 photons, and you can see there's a peak about 126 or so GeV. And here is going into the 4 muon channel, a very big peak. And by getting that ratio, you can show that it's truly a Higgs. And it was shown to be truly a Higgs. So the Higgs particle was discovered. And this means that there's a new structure in the universe. There's a new field out there called the Higgs field. That's another part of the universe. And this was a very, very important event when this particle was discovered. And so we have all these things. I won't go into this, but you see the Higgs field now is the part which actually brings the standard model together, because there was an important mechanism to essentially give mass to the particles. And now I don't have time to go into this. Some of the things that we're looking for at the LHC are something called supersymmetry for every fermion. The fermions have half integral spin, and bosons have integral spin. And the idea was that for every fermion there's a boson, every boson there's a fermion, and and there is a reason that you want to have such a thing, because it, first of all, in all theories which try to unite general relativity and quantum theory requires supersymmetry. It somehow involves supersymmetry. Supersymmetry takes care of some technical problems in particle physics, and it also helps unify the forces. And you see, for example, you would have a quark spin 1/2, a squark, a super symmetrical quark, spin 0, photon, photino, electron, ace electron. You see how it goes, and so that's a very important thing that they're searching for now at the LHC. It turns out that if you look at the top curve, there's the feeling that there's a grand unification scale in which the forces unify to one force. Actually, most physicists think, from theoretical points of view, that at the Big Bang there was only one force, and as the temperature decreased, these forces basically split, and this corresponds to energy. So at 10 to the 16th GeV, these forces will unify if you put in supersymmetry. So that's why people like supersymmetry. Then, of course, one would like to also look for extra dimensions. String theory basically involves 10 dimensions. There have been some theories which say that, well, maybe some of these dimensions extend out to observable lengths. In string theory, these 6 dimensions, 6 extra dimensions, only extend out to 10 to the minus 32 centimeters. So there's no possibility of ever detecting them. However, in some theories have suggested that some of the dimensions may go out as far as, let's say, 10 to the minus 18th, 10 to the minus 19th, 10 to the minus 17 centimeters. And CERN can find extra dimensions if they're bigger than 5 times 10 to the minus 18. So they're looking for extra dimensions. That would be a momentous discovery, to discover extra dimensions. And so there are many, many great issues. They discovered the Higgs. Is there supersymmetry? Do all the forces become one? In fact, the lowest energy neutral supersymmetrical particle is thought to be perhaps the cold dark matter. That's another thing. So they're looking for that. That's a good candidate. And so can you learn anything about dark energy? And for example, you can also learn about whether quarks are the smallest building blocks of matter. I'm sure there'll be breakthroughs of the type that we never even anticipated. See, many of these are what you call planned discoveries, but there'll be surprising things that nobody ever thought about. And that's where some of the greatest excitement comes in new accelerators. So it's actually a very exciting time in particle physics, and maybe some of you may join in this great quest to learn more about the world that gives us the basic structure of atomic matter. Thank you very much. Thank you for your kind applause.
And now I open the discussion. Please ask questions for Professor Friedman. It's your unique possibility to ask Nobel laureate.
Professor Friedman, thank you again for your lecture. You talked about particles having mass, and this year Nobel Prize for Dr. McDonald is for neutrino oscillations, basically proving that neutrinos have mass.
Yes.
So is that a new paradigm? Was it a surprise that neutrinos have mass, or was it just expected and now it's proven?
Well, you know, actually it wasn't expected because, you know, when I first started in this area of research, it was almost definitely thought that neutrinos have no mass. They were like photons. And so actually it is a surprise, and it's a great revelation, and the oscillations are an extremely interesting and important quantum mechanical phenomena. So that's a very, very good development in physics. And so the question is, now that they have mass, these masses are incredibly small. You know, you're talking about things between a tenth and a hundredth of an electron volt. And you know, all the masses I've been talking about have been described in terms of million electron volts. So what makes the neutrino mass so small is a very, very interesting theoretical question, and that there'll be a tremendous amount of research on this issue.
Professor, in present time, have you information about the highest value and good verificate of redshift of individual cosmological objects?
I'm not sure I understand the question. The
highest value of redshift.
Oh, the highest value. No, I don't know the answer to that question. What the highest value, what the deepest probe has gotten into right now. Unfortunately, I'm not really a specialist in this field. I just am interested, but that's a very good question, and I really will look into that because that's something that's been changing all the time. You know, the first picture I showed you, basically showing the galaxies, that was a very deep probe. That was actually probably 7 or 8 billion light years away, but I'm sure they can go much further back. But I don't know the exact number, but it's a good question. Sorry.
Mr. Professor, you mentioned quark confinement in hadrons.
Yes.
And could you make a comment on quark confinement? I mean, search for quark gluon plasma and recent experiments.
Well, you see, the thing is, what I said is quarks have to be confined to other quarks, but they don't necessarily have to be confined to a nucleon or a hadron in general. If you take, let's say, nuclei and smash them together with enormously high energies, what happens is that some of the nucleons will start fusing, and you'll get what this gentleman called a quark gluon plasma. And what that means is the gluon is the particle associated with the quantum chromodynamic force. And so you get this sort of this volume of quarks and gluons swirling around. And the reason is that you call it a plasma is because they are all charged. And so and basically you don't have the so-called color, mantle. And if you go inside there, basically you'll be near so-called colored quarks, and therefore it's like a plasma. And this has been observed at the LHC in terms of their heavy ion experiments, where they take gold nuclei and smash them against gold nuclei at very, very high energies. And it's a very interesting field.
I have a little bit personal question. How do you personally imagine quark? Like, it's energy, but I like to imagine things. So how can it be done? Or have you ever tried to imagine how it would look like?
I imagine them all the time. And no, to me, you know, even though they're point-like, I see them as little balls of color. So I take the color literally. So I have them, you know, I see them with having a charge, a little ball of something with color, and that's the way I see it. And I see, you know, I'll make in my mind, I'll make a nucleon with 3 quarks swirling around, and then occasionally a gluon goes from 1 quark, goes into a quark pair. Then basically the quark pair comes together, gives another gluon, which then attaches to. So you can actually picture these things. You know, my imagination is very much image related. So I see these things all the time. So.
Okay, one of your first slides, you had a time scale, and it started with the first timestamp was 10 to the power of minus 35.
Yeah.
And the comment was that at that point, fundamental particles were created, which is, you know, I don't really understand, because what happened before that? Well, are you saying that those quarks did not exist?
No, they you know, this is, you know, the actual details, you know, what happens in the interval before 10 to the minus 35, I think is a big mystery. The question is, before that, you know, in a certain sense, it could be that because the universe was so tiny, if you tried to make quarks before that time, they would annihilate immediately, and so you wouldn't have existence. You see, if you make a quark pair, what you're doing is radiation of some sort is making a quark pair. You know, and however, you can also, what you're making is a quark-antiquark. So the quark-antiquark can go back to radiation. Now, if you make a pair and there's no place to go, they're going to annihilate again. And so maybe the reason that you say that at 10 to the minus 35th, there was enough time for a universe to expand sufficiently, so if you made a quark pair, the probability of annihilation was very, very much reduced. I think that's probably what the reason is. But I'm not absolutely sure. I just thought about it right now.
I have a question about redshift, because it basically means that energy of photon is smaller at detection compared to when it was radiated. And there is also a possibility that this energy is lost during that long propagation of photon, or because there are some in optics we know scattering. Is there some experiment which rule out the possibility that this energy of photon was lost?
Oh yeah, no, you can show that from special relativity if you basically have a system in which there's a certain photon of a certain energy in a moving system, and then you observe it in the laboratory, and you observe the same photon. It's reduced in energy if it's going in the opposite direction of the photon being emitted.
No, sorry, I'm asking something different, because I understand this explanation of redshift, but my question is it possible that photon is losing energy during its propagation, because propagation of photon is so travels millions of years of years, that the energy itself is losing during its propagation?
I don't think, when you say losing, you know, in a certain sense, you have to lose energy in propagation, you have to excite something. And the question, if you don't have things to excite, the energy will basically be intact. And so we're talking about, actually right now, the universe is really quite empty, except for these fields and virtual effects. The virtual effects will not change a photon coming through them. But space is sufficiently empty, so the photon coming through space will not lose energy in propagating.
Another question?
You mentioned dark matter. Do you think it consists of some small particles that are quarks, or it could be some type of quark we don't know?
No, they know it's not, has nothing to do with atomic matter. There are theoretical arguments which are quite complicated, which indicate that dark matter has absolutely no relationship to atomic matter. And so there are two candidates today. One is the supersymmetric, something called a neutralino, which is the lowest energy neutral supersymmetric particle. That's one candidate. The other candidate is something called axions. And axions are very, very light particles. And they're there for a very technical reason, which it has to do with CP invariance in quantum chromodynamics, which is too technical to discuss here. But these axions are possibly the source of dark matter. And they, at one time, thought that perhaps neutrinos were the source of dark matter, but it turns out that the masses are not sufficiently high and the number is not sufficiently great to account for the dark matter. And it could be probably something totally different that we don't even know about. And that's some of the great excitement of science. You know, very often you think you're looking for something special and something different, but just something that you know what to expect, and what you find is actually something totally different from what you would expect.
Another question, please?
Okay. We now know that we have three families of quarks and the same leptons, electron, muon, and tau. If I remember right, if the number of those families would be different, then the theory would not be normalizable.
Yeah, there are some real problems with that whole business.
Am I right that there is now no argument having them both 3 or both 4 numbers?
It could be. Look, you know, there are. I'm not sure I know of such arguments, but I wouldn't be surprised. There are so many different theories out there about various things that I'm sure somebody is proposing something of that nature. But I mean, the so-called, to get rid of the so-called anomalies, you have to have this number. But again, there could be at higher masses new families, but they would also have to have what you call the cancellation of the anomalies, which cause troubles. But that's a very technical thing. So I really can't comment on that because I'm not familiar with these particularly new theories.
And does anything coming from the superstring theory that could shine some light on number 3 in this sense? Is there some argument going from the string theory that would shed some light on why 3?
There could be, but I haven't heard of it. I mean, I think from my impression is that string theory is not sufficiently advanced to actually make such specific predictions at these very low energies. You know, see, string theory is a theory at the so-called Planck scale, which is 10 to the 19th billion electron volts.
But at least you don't have problems with that renormalization or ultraviolet divergences, do you, with string theories? So it's not going like that.
Well, they think they've taken care of that, but again, I can't really comment on that specifically. I haven't really heard anything definitive from string theory which would really relate to specific phenomena, except for the points of view of having some structures that they point out. They think that they can actually produce structures of theories at lower energies, but I'd be surprised if they could show that string theory you could get rid of ultraviolet problems at low energies. I'd be very surprised, because you see they're extrapolating 15 orders of magnitude, more than 15 orders of magnitude.
I'm not a physicist, so my questions are maybe quite simple. As far as I understand, Higgs field is field which is present everywhere, including inside solid objects. Is that right?
Yes, everywhere.
Okay. More than 100 years ago, physicists abandoned the theory of ether.
Yes, yes.
So what's the difference? Because it strongly reminds me ether. It's present everywhere, kind of force, kind of field, including solid objects. Can you tell me about the main difference between this old-fashioned theory of ether, which has not been defined properly, and this properly discovered Higgs field?
Well, I think you know, you have to ask what properties were put in the ether. What properties would you say you would?
What's the main difference between the theory of ether and the theory of Higgs fields?
Well, let me just see if I can. You know, the truth of the matter is my memory about what the ether. See, the ether was basically a. It had no sense of relativistic invariance. I mean, you know, the fields you put in today basically are put in a relativistically covariant way, and I suspect that ether was, since relativity didn't exist in those days, it was just a field that you put in. But when you put in the Higgs field, as in all the field theories that basically tend to reflect what's going on. You know, we have fields of all kinds in space. That's where, you know, that's when you think about the field theory in general, you have other fields in addition to the Higgs field. These are all put in a way which is consistent with special relativity, with covariance. And I suspect that's probably where the difference, and because, you know, in a certain sense, the whole business about the ether had to do with the fact that you would get all kinds of problems associated with violations of special relativity with the ether, because it wasn't put in a covariant way.
Thank you. Another question, please?
I would like to ask, because recently I read some article that's saying that the current level of the Higgs field energy...
I'm sorry, my hearing isn't that good. Could you speak a little louder?
Recently I read an article telling that the current level of Higgs energy field is currently like placing us in a metastable state, like our universe.
Could somebody repeat that for me? I appreciate it, because my hearing is not as good as it should. I'm sorry.
Well, you were telling us about the Higgs field.
Yes.
And so far it has some like energy level. And nowadays it has like some like value of this energy. And I heard that it currently places us, like our universe, in a metastable state. So basically by changing the level of the energy value, so the universe can collapse or something like that. Is it possible?
I still I heard. I heard enough. I heard enough that I think I understand what you're saying, but I'm not sure. But let me just say a few things about that. One of the great problems in terms of the Higgs field, in terms of cosmology, is that it gives an energy density which is much too high compared to the cosmological constant, and we don't understand why the cosmological constant is so small, and you know, compared to something like the Higgs field, which basically, you know, if you have a field, you have a field energy density, and that corresponds to energy in the universe. And now the cosmological constant is you know, fundamentally is much smaller. So the question is, to have these compatible, you have to have something which shields the universe from the energy density in some particular way. And this is one of the great mysteries. Remember I said that the dark matter, the dark energy is much too small in terms of particle physics. See, the dark energy is basically a cosmological constant, and it's just too small to account for the Higgs. Was that the question? But I must say, these are great questions. These are terrific questions, and wow. Yes, please.
I can have one last question.
Of course.
Well, I don't know much about it, but I read that there can be some kind of a duality between small dimensions and very big dimensions, like cosmological dimensions and very small dimensions like string length scale.
Oh yeah, that's one of the things. Yeah, that's one of the things that has come out of string theory's duality is that kind of duality, and that's a very interesting thing. And there's a duality also between theories with strong forces and theories with weak forces, and that's one of the strengths of string theory is that they actually get hints about how to deal with theories at much lower energies. But the string theory itself is not a complete theory, and I think there's a lot of work to be done in it. And the other problem is that it's not clear that one can always confirm or will be able to confirm the predictions of string theory, because remember in my talk yesterday I said if you really want to get to an energy of 10 to the 13th billion electron volts, you've got, in terms of the current technology, you're talking about an accelerator which is as large as some of the orbits in the solar system, and it's a size comparable to the parts of the solar system, and that's an awfully big accelerator. And now string theory is at an energy 1,000,000 times greater than that. So you're talking about galactic sizes for current accelerators. Now I wouldn't say it's impossible in the future never to build such an accelerator, but there's another problem, is that the yields for various processes go down enormously as the energy goes up, roughly as 1 over the energy squared. And so you have to get also not only high energies but enormous intensities to get to such high energy. So it's a daunting challenge, let me tell you. And I never like to say never, but again, if I have to bet on it, I don't think we'll have an accelerator to get to the Planck scale.
Would you like to follow up on that?
Yes.
Can we look at supernovas for these kind of energies?
To what? To
supernovas. Exploding stars.
Yeah. No. So what do you want to do with the supernova? I didn't quite understand that.
Can we look at the energy levels in supernovas to produce the fields necessary to study the?
No. Because you can't. You can look at them, but you can't transfer the energy. There's no way to do it that we know of. And in fact, you probably wouldn't want to if you. I mean, if you got a supernova near the Earth, you would vaporize everything. So you have to be careful.
But I mean, the cosmological radiation from supernovas,
oh yeah,
neutrinos.
No, but yeah, but the thing is, you know, the real problem there is it's 1 over r squared in terms of intensity. So you basically give up a lot.
So thank you very much, Professor Friedman, for the colloquium. Thank you all of you for coming and for your questions.
Thank you. Thank you.